can hear you. So go ahead.
Okay, yeah, so I actually think this is a great, it was great to have the presentation right before this because I'm going to be approaching this in more from a finite element perspective. So it was nice seeing parallel computing used on the control side. I've been recently very interested in graphics processing units and how to accelerate the speed of computation, mainly for the finite element portion of the real-time hybrid simulation. And so I'm just going to talk about some initial speedups that we've been seeing, very preliminary. And I'm hoping that this will lead to a larger conversation about high performance computing and how that can enter into real-time hybrid simulation during the breakout sessions. And so hybrid simulation, we've seen this in every presentation. We have this laboratory setting where maybe we have something that we want to represent that maybe is too large to fully represent in a laboratory setting. And so we could supplement that with some sort of computational model in terms of making our boundary conditions more realistic and increasing the sophistication of whatever we're able to test. And then those two things are coupled together through the equations of motion, and you integrate that through time to then get a more realistic response. Now, the issue of this is if you have any sort of rate dependency and you want to operate this hybrid simulation in real time, you sort of enter into this real-time bottleneck that was really expressed very well in the presentation before this. And so we need this computational model to keep up with whatever we're doing in the lab. And so the typical approaches are you're going to approach the numerical portion in a simplified way or potentially a reduced order model. You can even use a machine learning physics-based approach, or you do some offline pre or post processing to minimize that computational time. But the entire idea of this presentation is how can we approach this numerical portion of the hybrid simulation while still maintaining accuracy, but having a higher fidelity model that's able to keep up with what we're doing in a laboratory setting. And so we have this real-time hybrid simulation. It allows us to really have a more realistic representation of complex structures if you're constrained by your laboratory space, but then you also have this computational cost on the numerical side. And so the question is, can we use high performance computing environments to really improve that computational part of the hybrid simulation? And so Jim Rickles, he was just asking some questions. This is actually a study done by him. We're seeing pretty high fidelity models in terms of the number of degrees of freedom. And this is really pushing the envelope in terms of the number of elements and the sophistication of that numerical model. But then the question is, can we even go further and include potentially soil structure interaction effects in these very, very large and complicated models while still executing a real-time hybrid simulation? So this was a study done at UC San Diego that looked into real-time hybrid simulation of nuclear power plants. So the base isolators were tested on the shake table, and they actually did use parallel computing with CPUs to make this pretty complicated model of the nuclear power plant feasible. And so this was sort of one of the first studies using parallel computing for the numerical portion of the model. More recently, we've been looking at wave structure interaction at Oregon State University and how to extend our wave facilities to test much larger and more complex systems. Now, the issue with any sort of fluid structure interaction problem is that real time is a pretty hefty constraint because you can't get the water, or if you're dealing with wind, to slow down, unless I guess you could change the properties of the fluid. But so we have to have our numerical model keeping up with the fluid in real time. And then if we're dealing with any sort of small scale constraints, then we're actually having to keep up with the model in faster than real time in order to meet similitude requirements. And so we did this test in late January, and we actually did use the OpenSeas SP, which is OpenSeas, the parallel version of OpenSeas. And so this was a 5-span bridge where the domain was decomposed and to run on multiple cores. And we found that 8 cores was sort of the optimum number of cores that we could use to run this thing in parallel and to meet the hard real-time requirements. We could sort of slow it down, but we still had to have, I guess, let me just rephrase, we still had to have some simplification of the numerical model even with this parallel computing platform. And we did find, like, why only 8 cores? As we increase the number of cores, you might not get the same amount of speed up. And that's because as you discretize the domain to be finer and finer, now you have all this communication between the cores that actually slows down the simulation time. So 8 cores was ideal in this case, and we still had to simplify the numerical model to run this in real time. And so one of the concepts that we've been playing around with is we have this complete structure. We can break it up into two, these hybrid substructures. That's a physical component and numerical component. And so one of the ideas that we've had is, well, can we leverage what's been happening in the gaming and machine learning domains in terms of graphics processors to speed up the computational part of the simulation? And so it's really a focus on the numerical portion. I want to make that clear, not so much on the controls portion like what we saw in the previous presentation. And so why you might want to do this is because there's been a pretty large increase in the performance of GPUs since about the early 2000s. Something that really was a game changer was in 2006, NVIDIA came out with a CUDA programming language. And so now, instead of these graphics processing units, which were traditionally used for graphics rendering applications, very, very customized chips, you had to, if you wanted to do any sort of general purpose computing on it, you would have to write your analysis code in a format that would meet that sort of graphics programming on the chip. But with CUDA, now general purpose GPUs became more and more accessible. And what we started seeing after 2006 is GPUs were using more and more for scientific applications. There was also the rise in machine learning, which is enormously parallel, so it was very easy to run on GPUs. Compared to having a server or a server room in terms of high performance computing, GPUs are relatively easily accessible. They're relatively cheap. Most common computers, desktop computers, have GPUs. Of course, you have to think about single versus double precision, but in general, they're relatively cheap and efficient. And then this is actually part of a larger move when we talk about computer hardware to go towards more and more customized chips. So the GPUs started out as a very customized processor specific for graphics rendering. It then became more general purpose, and now what we're seeing, and then you had Intel developments of the CPU, which was very, very general, could do a lot of different computations. What we're starting to see is very specialized chips for very particular purposes. And so this evolution of the GPU and sort of its application to scientific computing is a much smaller picture of what's gonna come in terms of having customized hardware for, say, finite element applications. Now, the difference between a CPU and a GPU is this. Now, CPUs have these pretty smart cores, and they're really highly optimized to form serial tasks. And they're pretty intelligent. Now, when you get to GPUs, what you're talking about is maybe a suite of much smaller and simpler cores, but they're able to do many tasks at once. And so the entire concept of this is maybe CPUs are parallel in time, where the cores are optimized to do these very specific tasks fairly quickly and high performing in that sense. GPUs are more parallel in space, where you're doing a lot of tasks at once. And so it's really a throughput sort of idea. Now, the concept of GPU accelerated computing in terms of finite element analysis has been applied successfully in other fields. Some of the first applications were in seismic wave propagation. You can see on the left here, it's been heavily used in hydrodynamics to speed up the computations of the waves. And then something that might be most applicable to what we're talking about here is there's been a lot of work done in real-time surgical simulations. Having patient-specific simulations, finite element simulations that can be manipulated in real time. And most of those have to do with large deformations of soft tissues. Now, the issues with this is if we look at these applications in other fields, and then if we want to apply it to, say, the typical hybrid simulation problem, or the traditional one, which is mostly earthquake engineering, structural applications, these three don't really have the same problems that we might see in a structural or solid mechanics approach. And the reason for that is if we look at seismic wave propagation, you're having a lot of elements, they're all the same. They might have some heterogeneous element formulations, but you're talking about the GPU being able to operate on each of these elements at once. Hydrodynamics is the same thing, a lot of finely discretized domain where each of the elements are pretty much the same. And then the real-time surgical applications, it's really dealing with really large deformations of soft tissues. So you're talking about a much different range of periods. And so the stability requirements for this figure on the right, these biomechanical applications, is significantly different than what we see in our structural problems. And so there has been some work that has sought to take sort of the traditional approach with CPU only computing and replace that with this GPU or parts of this finite element analysis for natural hazards applications with GPU computing. And what we've mostly seen is sort of a partial acceleration approach. And this is the same approach that's been used in OpenFOAM. They're trying to actually do something a little bit more sophisticated now, but the simplest approach to adding GPU acceleration to a typical finite element analysis is just to take the solver, which is solving AX equals B, and port it to the GPU. And so you have the CPU that's still doing your assembly, it still has your time stepping scheme, it has most of the finite element analysis. But when you're solving AX equals B, that's going to be run on the GPU because the GPU is really good at linear algebra. Now, the issue with this is every time information is passed back and forth between the CPU and the GPU, it's a bottleneck. And we know this constraint pretty well. Basically, there's a PCIe bus between the CPU and the GPU. There's also some different memory hierarchies where the memory for this data transfer tends to be quite slow because you're taking this information and you're porting it off chip. And so every time you pass information back and forth between the CPU and the GPU, you're handling a bottleneck. So one approach that you could do to alleviate this, so you're not passing information back and forth every iteration or even every time step, is to fully port the finite element analysis to the GPU. So no longer is the CPU really doing anything in terms of the analysis. It's just initialization of the domain, and then everything else would be on the GPU. And so, so this is sort of the traditional and partial acceleration approach that has been used to date. And then this figure on the right is what we could think of when we're talking about fully leveraging the GPU performance. Now, the issue with this figure on the right is that the GPU architecture is very distinct from what you would see with CPUs. And so if we're going to fully leverage the GPUs to accelerate our program, we actually have to rethink all these different portions of the analysis and reformulate them to run on GPUs. So your equations of motion are still the same, but how they're going to be solved is going to be completely different when you start porting these components to the GPU. And it's more than just a programming language. So learning CUDA, for example, to write programs on the GPU, it's actually the algorithms themselves. In order to utilize that massive parallelism, where you're doing a whole bunch of simple tasks at once, you really need to reformulate every step of the finite element analysis. And so we did a pilot study looking at linear elastic dynamic analysis, and fairly simplistic. I hope no one's going to ask me the details on this. This is a very preliminary study, but we were interested if we took a single core CPU and compared it to a GPU, what sort of differences are we seeing in terms of the assembly, assembling the equations of motion, solving it, and then updating it to move to the next time step. And so what we're seeing is that because the GPU is able to do everything at once, so in terms of assembling the equations of motion, each component of assembly can all be done simultaneously. That's sort of the high throughput associated with the GPUs. And so that means that as long as you have enough memory and enough cores on your GPU and you don't have to pass through it twice, you get fairly constant runtime that's independent of the number of degrees of freedom, which is pretty incredible. That means if you have a larger number of degrees of freedom, it doesn't necessarily result in increased runtime as long as you're within the number of cores for that GPU. Now this still needs to be refined and optimized, but this is kind of an interesting take on how to think of runtimes in terms of the finite element analysis. Now we did see a difference between a single CPU core of about 15 times speed up, so that's fairly remarkable. The issue here is that the solver highly depends on the number of degrees of freedom and can't necessarily compete with the CPU. And really, when we think of a finite element analysis, most of our time is being spent on solving that AX equals B. And so this is very preliminary, it's very promising, but really these algorithms need to be refined. They were not fully optimized in the study. It's a linear elastic model, so really when we start talking about nonlinearities on the finite element side, that's where this 115 is probably going to reduce to maybe 5 times speed up, or hopefully 10 times speed up, based on other studies. And so a lot of things aren't implemented here, but it's sort of a promising way of looking at how much you could potentially accelerate what's happening in the finite element side of the hybrid simulation in terms of GPUs. So let's look at this a little bit further in terms of what portions of this GPU acceleration would need to change. So this is sort of a look at a typical finite element formulation from a structural analysis standpoint, which it's not necessarily a hybrid simulation perspective on it. It's just traditional finite element. And then I'll talk about a little bit how this would change for hybrid simulation in a second. So you have a CPU and a GPU, and you still need the CPU. You're basically controlling what happens on the GPU via the CPU. So typically you start by pre-allocating some sort of memory on the CPU, and this, I'm sorry, I should say GPU on the right-hand side here, and you'll initialize the domain on the CPU and then copy all those properties to the GPU memory. And really this would be before our finite element analysis really starts. And there has been a number of studies that have actually looked at sort of doing the mesh on the GPUs, but for a lot of our problems, we're really more interested in performing the analysis part of this on the GPUs. And so you can imagine building the domain on the CPU and then basically loading that onto the GPU memory. So that's sort of step one, very CPU driven. And then once you're on the GPU, that's when you start looking at your analysis. And so one component of this is the state determination. And so in our problems, we typically have a number of different numerical elements. They can all have varying degrees of nonlinearity. I'll talk about why that's a problem for GPUs in a second. And you use that to sort of set up that time step. And then you take the different element contributions from each of those different element formulations, and you assemble them into your global stiffness and right-hand side force vector. So there's an assembly part that also is going to be run on the GPUs. And then once you solve that, or once you set up that left-hand side and that right-hand side, you have a solver that solves AX equals B. And then, of course, you have your integration in time. So how do you move from time step I to time step I plus 1? And here again, I'm showing a pretty traditional approach to finite element, where you might have an implicit integration scheme. And so that's going to be associated with iterations where you're doing that assembly and solve multiple times within a time step. And then potentially committing the solution states once you have convergence to within some tolerance, and then moving on to the next time stepping integration scheme. And then something to note with the GPU side is that there are memory constraints associated with the GPU. Those are becoming better and better as the newer GPUs come out. It was much more of a bottleneck in say the early 2000s than it is right now, but you might simultaneously, as you're moving to the next integration phase, you might want to keep on offloading those previous states to the CPU. So let's talk about these challenges. I sort of opened up, that was the traditional approach here, which really isn't set up for GPU acceleration. And so if we want to think about porting the entire analysis to GPUs, we actually need to reformulate pretty much every single one of these steps to be GPU compatible. And so let's talk about state determination.
To see if we wrap up in the next couple of minutes, we'll have time for questions.
Yeah, of course, of course. I'm close. So let's talk about state determination. There's a number of challenges associated with this. First, I'm talking about how we have varying element formulations, so heterogeneous element formulations. And also each of our elements could have varying degrees of nonlinearity. And then each of those materials that we use often have conditional if-else statements. Now, the issue with having this on GPUs is that this is really formulated for single instructor a single instruction, multiple data paradigm, which means that it's really good at performing the same task on a whole bunch of different cores. It's not necessarily good at doing different instructions like you would see with the CPU. And so the fact that we have different element formulations means that we have to rethink on how to have this on the GPU. The if-else statements associated with nonlinearities, well, how the GPU sort of approaches that is it might take both branches of the if-else statement and do them both at the same time. So if it's elastic versus inelastic, it'll actually do both of those and then choose one at the end. So that sort of thread divergence is also an issue. And so what the GPU does is it takes your for loops, and each iteration of that for loop is basically executed at once. And an abstraction of that for loop is via threads. And those threads, if you're using NVIDIA GPUs, are then collected into warps where all the threads on a single warp are executing the same instruction. And then those are associated with thread blocks, sort of collected together in thread blocks, which are all still, that are all synchronized at once. And then we have grids which are all executed independently, all having different instructions. And so how you might approach this is you can think of having each numerical element, which has its own element formulation, but same instructions. You can sort of use a batch approach where all the same elements are sort of corresponding to a single instruction. And you can also take each element and potentially put it on a single warp to deal with different nonlinearities. And so this is just an example of how you would need to recognize the hardware underlying the finite element analysis in order to port everything to the GPU. Another issue has to deal with the coupled equations of motion and sort of the unstructured meshes that we tend to have in finite element analysis. So as we take each of our element stiffness matrices and sort of assemble them into the global stiffness matrix, we're accessing multiple memory addresses at once. So the issue with this is that every iteration of the for loop on a GPU is done at the same time. And so there can be race conditions as you're trying to add element contributions to the global stiffness matrix. There's another part of this as well that needs to be thought about. In terms of the hardware memory hierarchy, there's also different memories that are slower versus faster on the GPU. So if you're looking at the threads, which are communicating within a thread block, those are using shared memory, which is relatively fast, and then the thread itself has its own small bank of local memory. It's also fairly fast, but as you start getting these blocks into different grids in terms of global memory, which is typically how each of the blocks within a grid are communicating amongst each other, and also how you're communicating with the CPU, we're looking at something that's significantly slower. And so as you take these local stiffnesses and put it in the global stiffness matrix, you're looking at sort of global memory concerns and making sure that access to global memory in terms of having an unstructured mesh where you might have multiple elements sort of sharing the same degrees of freedom. You want to make sure that as you access that global memory, that you have memory coalescing, where basically when you have global memory access, everything is aligned and sequential. And so what this requires is complete restructuring of the information in your mesh prior to even performing the analysis. And this is huge when it comes to performance on the GPU, is making sure that memory access is as fast as possible and sequential and aligned. The other one that I want to point out is issues with the solver. So solving AX equals B. I'd like to point out that this is something that's very specific to implicit integration schemes. And so typically when we look at solvers in structural analysis for natural hazards, we're using direct solvers. The issue with that is that they're not really easy to run in parallel on GPUs. And so what you might see in terms of the solver on GPUs is a lot of iterative solvers. So preconditioned conjugate gradient is most often used in the literature. Now, the issue with this is that it's highly problem dependent. So if you're going to precondition that iterative solver, it's going to depend on your problem. And it also highly depends on the size of the model. So for example, ANSYS Mechanical, they've ported just the solver to the GPU, and they're saying that to achieve speedups on the solver with respect to multi-core CPUs, you really need more than 500,000 degrees of freedom, which is a lot for our types of problems. And so one way to mitigate this effect is maybe look at something where you don't have the solver integration scheme, where you just have matrix multiply, which the GPUs are very good at. And so then we start talking about which integration scheme you could potentially select. And this is where real-time hybrid simulation can really play a role in this, because we're pretty good at formulating integration schemes where we have unconditionally stable methods that are fairly accurate, that have numerical damping, that might be ideally suited to the matrix multiply that we see that the GPUs are really good at. So I have this real-time surgical applications that I talked about earlier. The issue with using really any of the formulations that they've done in that world for us in real-time hybrid simulations is that these are very soft tissues that are undergoing large deformations, extremely different stiffness properties, and really what they're using is explicit Newmark and central difference, which are going to have major stability concerns when we apply it to real-time hybrid simulation. So a lot of these other applications, while very promising, still need to be rethought of in terms of how we want to approach our RTHS requirements. And this will be my last slide that I'll show. Sort of extending this to real time is a problem on itself. The previous presentation sort of mentioned how multi-core computing is a problem in terms of load balancing, also with determinacy. And so there's a number of challenges associated with just using multi-core in general in parallel processing for real-time hybrid simulation. And so it's difficult to guarantee concurrency, especially on the GPU. You don't really have control of the order of which things are being done. The cores could have some latency, especially when you're communicating between the GPU and the CPU, and most of our controls and our data acquisition system are going to be CPU dependent, so they're not going to be able to be loaded onto the GPU. So you're going to have to really be careful about how you're communicating with your finite elements on the GPU and the remainder of your hybrid simulation on the CPU. There's a number of issues associated with load imbalance that kind of has to do with the heterogeneous element formulations and the inelastic behavior that we tend to have during earthquake simulation of structures. And there can be high hardware dependence in terms of how fast your GPU is. And so I'll just kind of end with that and just kind of note that even if you can accelerate the finite element portion of this hybrid simulation, there's still this communication bottleneck that could be a concern because you still have to communicate with the CPU. So I have other slides, but I think I'm over time because I see your face. So, and I was talking so fast too.
Okay, so now we've probably got about 10 minutes for questions, and then we're going to go straight into the breakouts. We'll have about 40 minutes for the breakout sessions, and then we'll all try and be back in the main room by 4:55 Eastern, just before 5 Eastern. So we've already got one hand up. Oh, you going? Jim, did you have a question?
Yeah, I had a question there, Barb. Very interesting presentation. You and I have talked about this many times. I think one point to emphasize, and you did do this at the end, is that and I wanted to ask first by starting off with the question, you mentioned fluid dynamics is very conducive towards using GPUs, but not structural dynamics. And I guess what I thought I wanted to ask is that because, you know, there's a lot of explicit formulations for fluid dynamics, finite differences, but are in structural dynamics, you're thinking implicit, that's where that statement is sort of based on, that implicitly the AX equal B, you have to iterate till you converge, and no telling how long that will take. Is that really the basis for that statement there?
Somewhat, it's really more of the element formulation. So GPUs do really well when they're doing the same thing across, you know, a massive data set. They're really good at that. And so if you think about really finely discretized problems like fluid mechanics, where you have to have a really spatially speaking, very fine discretization, then each of those elements are having the same instructions, and that can all be done at once. And so the GPU is really good at that. Whereas if you have structural problems where oftentimes we're not dealing with higher order elements, for example, if potentially we could see much larger speedups when it comes to shells or brick elements, but we're not dealing with that really fine level of discretization that you would need for a fluid dynamics problem. Another thing that may come into play, and I'm less familiar with this, is they do have sort of a prediction correction type integration scheme where they predict velocities and then correct pressures, which I believe is still very, very iterative. But if you can do the matrix calculations of those iterations fairly quickly, then you can go through the iterations more quickly. Another example of GPU computing that has been very successful is in the molecular dynamics realm and sort of chemical kinetics. And that's again because all of your elements are really the same. They're all receiving the same instruction. And because of that, the GPU can operate on all of them at once and fairly reasonably. On the chemical side, they still do a lot of hybrid CPU, GPU driven computing. And I do believe that portions that aren't really compatible with the GPU still reside on the CPU. And sort of it's like a multi-grid type method of integration.
Okay. No, that's okay. I didn't mean for you to elaborate that much, but
oh, sorry.
No, it's okay. One other question is, you know, we've migrated towards explicit schemes primarily because of exactly what you say. You really, especially for highly nonlinear problems, it's very difficult to formulate sometimes the stiffness matrix, but it also takes time. But on top of that, the iteratively AX equal B, you really can't avoid that, and you can't leave unbalanced loads there, right? If you try to carry them over, it's going to create noise and that stuff. So I think the issue about explicit schemes that are unconventionally stable, and when you have explicit schemes, dissipation, numerical controlled damping is very important because of the effect of the state change within the time step.
Right. And
if it's truly explicit, it's all matrix multiplication. There's no inversion at all. It's all multiplication, go pretty quickly, I think. So
right.
And see how that works out for us.
Well, and really, when you look at the literature, most of it is with explicit time integration schemes for that exact reason. Implicit becomes interesting because it potentially is more feasible provided your iterations are done in a much smaller time scale. And so you think maybe you do have to perform iterations, but maybe the iterations are being conducted significantly faster than what you would get in a typical hardware environment. And so you can get away with having some iterations or multiple iterations. One of the things that and I'm not saying I have actually tried this out, so I don't know if it would work, but that's something to think about that might make some of these implicit methods a little bit more feasible and still get the unconditional stability. But I think the explicit approach, in my mind, is the way to go. Something that's kind of interesting is,
sorry, Barb, you answered my question. I didn't want to take up time from Dr. Kwong, who I think has a question as well. But
okay.
Yeah, we've got 2 more questions just to finish up.
Sorry, Barb. Thanks.
No, that's.
So, Osong?
Sure. Thanks a lot, Barbara, for a very interesting presentation. It's very impressive. I have one quick question. I saw one example where you use OpenSys to run simulation, probably a hybrid simulation with a wave and bridge instruction. Was it a hybrid simulation or not?
It was, yeah, it was.
My main question was that what is the size of the model that you are solving in OpenSys based on the way you presented it? The size of the bridge looks small with a few frame elements.
So the issue with that model wasn't, it did have, like, it wasn't really a size, it was more of a complexity issue. And so there was a lot of number crunching. It had a lot of inelastic behavior sort of embedded in it. And the material formulations were pretty complex, and it was a 3D model. And there was torsion involved and things of that nature. Now, the actual size of that model is a really good question. You know, I don't do any of this stuff. My students do it now. But I can say that if on a single core CPU, it was running at about an hour. And then we simplified the model, and then we ran it on 8 cores, and we could get it about in real time. Now, I'm talking soft real time. So we were using this sort of a 3-tier architecture that you see on the lower right here. So it was using, I think we had a couple instances of predictor corrector where that kicked in because the computational model wasn't fast enough. And so I might have presented that work here. You probably won't ever see me publish it because I think we have to look at it again, because I'd like to get it to the point where we don't have any sort of predictions corrections involved.
I see.
But it was this 3-tier architecture.
Without taking too much of the time, in fact, several years ago, I also tried to see the scalability of OpenSys SP by compiling it, for supercomputer and run the large DOF analysis. I had the same experience. Over 8 cores, I cannot get any performance more than that. And then the second follow-up small question is, what is the update rate of your hybrid simulation when you use OpenSys SP and run real-time hybrid simulation? What is the update rate?
So our controller is running at 2048 hertz, and then I think the time step we were using was 10 times that.
So about 0.02 millisecond. About 20 milliseconds.
Well, now you're making me do math, and it's a Friday. No, but yeah, it's 10 over 2048 is what we were using.
I know that.
And the issue is we did try, because we wanted to make it a little bit better, we did try 20 over 2048, and it wasn't accurate. We didn't get the degree of accuracy that we wanted. So the time step was too big for the integration scheme.
All right, thank you.
Yeah. All right, Johnny, we've probably got about 3 minutes for your question, mate. So hopefully we can fit you in.
Hi, Barbara. Nice presentation. I have some questions for you. So regarding the real time or the platform that you're using with the CPU, GPUs, what is the impact of this communication latency between the CPUs and GPUs into the performance of the simulation or the experiment you were running?
Yeah, and I should note that we actually haven't performed a hybrid simulation with GPUs. So this is all like theoretically you could make this work. So that's a huge bottleneck. And you're gonna have to make sure that whatever communication that you're doing with the CPU is relatively synchronized with what the finite element analysis is doing. And so you can have sort of different portions of your operations on the GPU that are communicating with the CPU while the finite element analysis continues to move forward. And so there's a way of having that communication sort of interleaved with the other processes that the GPU is trying to conduct. But really, that is a huge bottleneck when you're then thinking of communicating with the laboratory controller and data acquisition system. And so what we are using for the CPU-driven approach is that we have scramnet and fiber optic cables, which might still do the trick, but might just be the new bottleneck where that just takes too much time, no matter how fast your finite element analysis is running. So another thing we've been sort of playing around with is, could we use EtherCAT, which could potentially be useful. Someone did, so that is the major concern that I have with the GPUs, is that you really don't have that determinacy. And so to me, it really has to somehow communicate with whatever CPU portion of your system is there, and you're dealing with the same communication bottlenecks that we have in hybrid simulation in general. So I think this is the #1 concern, if you can get the GPU portion of the system set up. So. But you have it all on one computer. So you don't have that sort of communication issue, at least when you're doing the CPU, right? So you have the parallelism embedded with the controller all on the same machine. What we're proposing here is that we have 3 separate machines where the GPU or the finite element analysis is really doing its own thing, totally separate from what's happening on the controller side. And so it's more of a, whenever that information is available, it can be sent to the controller. So it's a little bit of a different perspective. So for communication for us is huge,
Mhm.
and
Okay.
definitely an extreme bottleneck. I don't know. Did that answer your question?
Yeah. So just to comment, so we do have some latency between in the communications, because in the CPU's machine we have, let's say, 2 sockets, and each socket has 12 cores. And when we use the first socket and then we use the first core of the second socket, this communication between sockets has an impact on the performance as well. But that's why my question was if there's an impact between GPUs and CPUs communication latency.
Yes, and that's going to be there no matter what, regardless of whether you're using the multiple machines.
Mhm.
It's the same problem. And then there's on top of that, there's the memory. The memory is a lot slower in global memory. So if you're trading information between the CPU and the GPU, it's going to be slower no matter what, because it's just going on chip. So yeah, that's all. So if you can minimize that in any way, that's very helpful.
Okay, one quick question, last one. What parallel platform are you using for this for this approach? I mean, OpenNP or Thread?
So the GPU portion is CUDA.
Yeah.
So that's all CUDA based. There has been a lot of recent work that profiles code to run on GPUs automatically. So OpenACC, I haven't used it, but OpenACC will actually take your C++ code and then basically take all its for loops and then run it on the GPU. So that's definitely, but this is a totally CUDA environment that we've been using here. So everything's is pretty much being rewritten from scratch.
Okay, thank you.
Okay, great. I know I have lots